Today we'll determine the solubility product constant of calcium iodate. Calcium iodate is a salt which, as many others, when dissolved in water, it dissociates into its corresponding ions. In the case of calcium iodate, you produce 1 mole of calcium ion and 2 moles of iodate. In the determination of the KSP, you equal this to the concentration of calcium times the concentration of iodate squared. If you substitute this with variables, you have S times 2S squared, which is equal to 4S cubed. Now, we'll also look into the common ion effect, which involves having an ion of the salt already present in the solution. This is important with the Le Chatelier's principle, which states that you will have a decrease in solubility as you already have one of the ions present in the solution. Before starting the experiment, make sure that you put on your goggles, your gloves, your lab coat, wear closed-toe shoes, make sure that your pants cover your ankles, and if you have long hair, please tie it back.
For this experiment, we will be using a saturated solution of calcium iodate in potassium iodate of 0.01 molar, a saturated solution of calcium iodate in water, sodium thiosulfate 0.05 molar, a standard of potassium iodide, and hydrochloric acid 1 molar, starch indicator. For the glassware, we'll be using a 50 ml burette. For the titration, 2 beakers. We're going to be using the big beaker of 500 or 250 ml for the waste of your titration, and small beakers to get the reagents. For the titration, we're also going to be using graduated cylinders of 110 ml, and we're going to be using an Erlenmeyer flask of 250. For this demonstration, we're going to be doing the common ion effect experiment, meaning that we're going to be using the calcium iodate solution in 0.01 molar in potassium iodate. First thing you want to do is to set up your burette. Your burette looks like this. First thing to do is make sure that your burette is closed before trying to clean it. To clean it, you need to get your solution that you're going to titrate with, in this case sodium thiosulfate, put a little bit on a small beaker, put it inside your burette, just like 1 ml, it's fine. Now you're gonna take it like sideways and you're gonna rotate. Make sure that the solution is touching all the way to the 0 mark. Once you rotate it once or twice, you're ready to decant the solution. To decant the solution, please put it in the safety holder. Put the waste beaker underneath and open the burette to let the liquid flow. After all the liquid is out of your burette, you're ready to fill it up. I already have a burette on this side filled out, and I'm just gonna refill it all the way to the 0 mark. Once you have filled out your burette, you're ready to start your experiment. First, you have to make sure that you have the correct amount of the chemicals you will be using. For your saturated solution of calcium iodate, we're going to be using 10 ml. To get your 10 ml into your graduated cylinder, you need a small beaker and a pipette. Make sure that you're not contaminating this stock solution. For this one, we're going to be using 10 ml. For the hydrochloric acid, we're going to be using 10 ml. For your starch indicator, you're only going to be using 5 ml. For your potassium iodide, you're gonna be weighing in a weighing paper or a weighing boat 2 grams of potassium iodide, and you're gonna be getting a big graduated cylinder with 50 ml of water. Once your burette is ready, you're ready to start your titration. Get your Erlenmeyer flask. Then after that, you're gonna get your 2 grams of potassium iodide, and you're gonna put them inside the Erlenmeyer flask. Next thing to do is to grab the 50 milliliters of water, and you're also gonna add them inside the flask. After that, get your HCl, hydrochloric acid, and add them in the flask. Finally, you're gonna add a saturated solution of calcium iodate in water, and your solution should turn into a red brownish color. Make sure that you mix the solution well before starting the titration. Once you're ready to start your titration, first thing you need to do is to place the Erlenmeyer flask underneath the burette, and you're gonna open it slowly. Make sure to record that you're starting from 0 and then record the final level that you reach after the titration is done. You slowly open the burette to let the flow go so you won't miss the titration. With one hand you're mixing it, with the other one you're making sure that the burette flow is not too fast. Keep an eye on your solution because the color change should happen at any moment. Once you have reached a yellow color, you're ready to start the titration and record the amount of sodium thiosulfate that you use for the titration. After that, you're gonna add the starch indicator into the titrated solution, and your solution should turn into a dark blue-black color. After you mix it well, start the titration again, and remember to do it slowly because the change is gonna happen really fast. So you're gonna go from this color into a colorless solution. You did a titration.
So let's look at the explanation for the reaction and how we determine the KSP, which will help us determine the molar concentration of calcium and iodate in solution. So the formula that we are using for the first part is iodate plus 5 iodide ions in solution plus acid produces 3 iodines plus 3 water molecules. Once all of the iodate has been transformed into iodine, we can then do the second part of the titration, which is to convert the iodine back to iodide using thiosulfate and an indicator. For every 2 thiosulfates that are titrated into the solution, producing 2 iodides, it consumes 1 iodine. From the first equation, we see that 3 iodines are produced for every iodate. Therefore, for 6 thiosulfates used in the titration, we have titrated 1 iodate ion. So when we figure out the calculation for iodate concentration in the solution that we started with, we will first have the amount of thiosulfate we added in the titration divided by the amount of iodate solution that we began with, multiplied by the concentration of the thiosulfate solution that was in the burette when we titrated it, multiplied that ratio that we just talked about, which is 1 mole of iodate ion to 6 moles of thiosulfate. Once we add all these numbers in, we now determine the concentration of iodate in solution. So here's the chemical formula for our beginning salt, which is calcium iodate. There's 1 calcium and there's 2 iodates because of the charges on both chemical species. So if we want to determine the solubility constant, which is the amount of calcium iodate that will go into solution, we will have calcium times iodate squared. The reason it is squared is because there's 2 iodates for every 1 calcium. If we let S represent the molar solubility of calcium iodate in units of moles per liter, the concentrations of calcium and iodate ions will be related to the molar solubility by S equals the concentration of calcium, and 2S is equal to the concentration of iodate. If we then substitute an S for the concentration of calcium and the concentration of iodate, we will have KSP equals S times 2S squared, which will give us KSP equals 4S cubed. So once we have determined the concentration of iodate through titration, we can then calculate the concentration of calcium in our initial solution, which when set to S will allow us to calculate the solubility product constant for this experiment.